All right. Good morning, everyone, or at least good morning from where I am. So, welcome to the second semester 2 week of Qubit by Qubit. So today we're going to be taking a little bit of a different path from what we talked about last week. Last week was all about programming and NumPy, which is all fine and good. But for the next couple of weeks, actually, we're going to be returning to more of the math behind quantum mechanics. So more sort of like fundamental physics that is going to gradually lead up to a more thorough understanding of what we're talking about when we consider qubits and gates and all that kind of stuff. So hopefully this gives us a more solid connection to the so-called real world, instead of just all of these sort of arbitrary and very abstract matrices and vectors that we've been dealing with so far. So a quick look at the program for today. We'll start off just with a very quick reminder of logistics and ground rules around the course. Then we will go into our Canvas attendance quiz. Then we'll do the pre-lab Zoom feedback, questions from last week, lab content, post-lab Zoom feedback. All of this is a pretty standard look for a typical lab. So some quick logistical reminders. The homework for this week is the week 11 homework, and it's due, like all of the homeworks are, on Sunday at 11:59 p.m. Eastern Time on Canvas. A quick reminder that Canvas contains all of the required course information and materials. So for example, I sent out the slides and the code from last week on Canvas. Hopefully you all received that okay. Just a reminder that TAs don't answer questions on Canvas. That will be Piazza. But if you have any sort of course administrative issues, you lose access to Canvas or you can't get on Piazza or whatever, any of those types of things, student@qubitbyqubit.org is the email you want to be contacting. And then final note is just Piazza. Obviously, we can't address every single question in lecture, lecture or lab, much as I would like to. So instead, we have Piazza set up, and us TAs will often be checking Piazza and leaving answers to questions on there in case we don't get to them in labs. Okay, I went over that fairly quick, but actually I am just gonna make sure everyone can use the chat. So if you have any questions as I'm going through this stuff, please feel free to just throw it in the chat and I'll stop and address it. But I'm gonna try and go pretty quick just because I wanna get to the actual content for this week. Okay, so the Canvas attendance quiz. Log on to Canvas. We are lab number 1, as I said, always pretty easy to remember. Hello from Canada. The quiz password today is 9843. So go ahead, open up your browser, fill out the attendance quiz. Just as a reminder, this attendance quiz passcode thing, 9843, it's always in the bottom right of all of the slides. So even if you pop in a little bit late, like no worries at all, you can always fill it in based on that attendance code in the bottom right. Yeah, see, I knew it. It's probably not morning for like most of the people here, but good day to all of you, whatever time it might be. All right, so the question today is just, if you participated in the fall semester of Qubit by Qubit, how has your confidence in your STEM skills changed? So one of the answers to this question on Canvas is just, I was not in Qubit by Qubit fall semester, and that's totally fine. But if you were, we were just curious to see how your STEM skills have changed. One of the goals of this course, beyond explicitly teaching you quantum computing, is just generally to increase your confidence in STEM, because kind of by the nature of quantum computing, we're going to be touching on, I mean, you've already seen, we're touching on math, we're touching on physics, we're touching on computer science. So we're hoping that you just gain more confidence in all of these areas through this introduction to all of them kind of at once. It's a lot of content, I know, but hopefully it's exciting. All right. So let's hop into the pre-lab Zoom feedback. So I'm going to pop up a poll on your screen that has options 1 to 5 for how you felt about this week's content. 1 being you really don't understand anything, sorry, all the way up to 5 being that you really feel like you understood this week quite well. Cool. Yeah, so this just gives me some sense of how I'll pace myself, and And actually, one other thing that I want to get in the habit of doing, if there are any specific topics from this week that you think you are having particular difficulty with, feel free to throw those in the chat. So just as a quick heads up on what we're going to be covering, well, actually, I can just go to the next slide and you'll see. Some of the things we'll be covering is, well, this entire lab is basically about the double slit experiment, right? That's what we're going to get to at the end. But all the stuff at the beginning is just sort of prerequisite material for ultimately discussing the double slit experiment, which is one of the sort of fundamental experiments to understand and to talk about quantum mechanics. So if there's any of these topics that you would like me to spend a particular amount of time on, please feel free to throw that in the chat. Okay, quantum computing basics. I can go over quickly. Yeah, I can go over that quickly for sure. All right, so a quick overview of what we're talking about today. I mean, I kind of just said it, but most of today is going to be the double slit experiment. But the first half is going to be sort of prerequisite material building up to that. We have to understand waves and particles to understand what the double slit experiment is, and most importantly, why it's so surprising. The optional content today, which as a reminder, I always do in this lab, but I will try to make sure that I get through all the required content, hopefully on time. The optional content is just a little bit of an extension on why the double slit experiment matters with single electrons and sort of how that adds to our understanding. Okay, so a few of the things that people are saying in chat: Schrodinger equation, Hamiltonians. Okay, sounds good. I will try to throw some of that in, absolutely. All right, let's get started. Oh, actually, sorry. So quick clarification from last week. This is actually something I think I already addressed in our last lecture, but this was a common point of confusion for a lot of people. Just the difference between defining NP arrays with double brackets or single brackets. Just as a quick refresher, this notation over here where you use double brackets, that allows you to be explicit about defining row vectors or column vectors. So in this case, I'm defining a row vector. I can also define a column vector by doing this. Now, this is a lot of brackets and it takes a while to write out. I totally understand that. But I would suggest that everybody go with this double bracket example just because it provides the closest sort of relationship to the way that we've taught linear algebra. It is perfectly valid to use this form over here. I'm just not going to go in. I'm not going to spend very much time explaining what it means or when to use it. It's kind of just a shorthand. And once you get more comfortable with NumPy, you can start using it more. But certainly as we're starting out, I would recommend just always being explicit with your array dimensions by using double brackets. Okay, so let's do a little bit of motivation on why we care about waves and particles in the first place. The first half of this lab is going to be basically about waves and particles. Now, I'm going to try and explain this through three statements. The first is that qubits are made of objects that show wave and particle-like behavior. Now, we've spent a lot of time discussing the linear algebra of waves and particles, but we have never really explained what it would be like if I were to place a qubit in your hand, right? What is a qubit? We might have mentioned it a couple of times, but the best definition for it is that qubits are objects that show wave and particle-like behavior at the same time. And so we'll talk a bit more about what that means, but the basic idea is that to understand qubits, you have to understand both wave and particle-like behavior, because that's kind of the definition of these things. The second statement is that quantum mechanics is the mathematical description of objects that show such behavior. So it's the description of objects that show wave and particle-like behavior. The reason we need quantum mechanics instead of just kind of regular physics, classical physics, is because we needed a new mathematical framework that captures both waves and particles. If you look at just classical physics, these two objects are treated separately. You have some equations that apply to waves, some equations that apply to particles, but nothing that really brings them together. The final statement then is that qubits and quantum gates and pretty much everything in quantum computing is governed by the rules of quantum mechanics. So we kind of have this linkage going on here where wave and particle-like behavior is described by quantum mechanics, and then qubits and quantum gates is also described by quantum mechanics. And so that's why we want to talk about wave and particle-like behavior, because at the end of the day, that's going to give us insights about quantum computing. So let's start off with a bit of an exercise. Hopefully this is a good lead in for everybody. I'm just gonna throw some images up on the screen, and I'm gonna ask you to think about whether you would consider them to be a wave or a particle. Now, none of these are meant to be trick questions, just as to get that out of the way. So we'll start off with, if I drop a pebble in a pool of water, there are ripples that come out from the center. Would we consider that to be a wave or a particle? Right, so everybody is saying wave in the chat, which would be correct. You know, I mean, we literally call them waves, and they sort of propagate out from the center where you drop the particle. They get bigger in all directions, you know, all that kind of stuff. All right, second one. Oh, sorry, I messed up the positioning there, but what we're aiming for here is the planets in the solar system, right? So if you take the Earth, for example, would you consider the Earth to be a particle or a wave? Again, correctly, everybody is saying that this would be a particle, right? So just brainstorming sort of how we know that, particles are things that have, you know, definite positions. We know where the Earth is. It doesn't really propagate out. You know, it's a thing that exists at a single location. How about this? If you took a piece of rope in like a gym or something, and you sort of wave it up and down, right? What is caused on the rope here? Would you consider the rope to be a wave or a particle? Again, everybody is saying it's going to be a wave. I'll go a little bit faster, but final example, soccer ball, or I guess for a lot of people here, football. Would a football be a particle or a wave? Again, here, a football is something that has a definite position, it has a definite velocity, all that kind of stuff. And so we would consider it to be a particle. Now, as some people are pointing out, there is a way in which we can see that these things are both, and we'll get to that in just a moment. But for now, I want to focus on sort of the intuition of how we came up with these answers. So I'll ask the question, how did we know that each of these was a wave and a particle? So let's just sort of brainstorm some of the properties here. I'll start off with waves, right? One of the defining characteristics of a wave is that it has some kind of repetition, right? If you look at the pattern on this rope as a person is moving it up and down, if you look at any individual point on the rope, it goes up and down sort of in a repeating fashion, right? And this is a characteristic of waves, is that they have some kind of repetition associated with them. And with that repetition comes a bunch of different quantities. It means we can define something like frequency, right? The frequency is just the rate at which that repetition happens. Another characteristic of waves is that they have, well, again, because of this repetitive property, you can track the physical distance between any two repetitions, and that is going to be our wavelength. What about a particle? Well, I already alluded to it before, but a particle has a definite position, and that's sort of the key defining characteristic of a particle. You can point to a particular location and say with certainty that is where the particle is. Whereas with a wave, you know, you can tell where any given crest of the wave is, as an example, but you can't really say where the wave as a whole is. A second defining characteristic of a particle is that it has some mass. So again, with the Earth, I can say, what is the mass of the Earth? With a wave of water, I could ask what is the mass of a water molecule, but there's no real sense in which the wave itself has a mass. Now, finally, just to kind of round this out, there are some properties that make sense for both waves and particles. One of those is the speed or velocity. Right, so the speed could be the how fast is the crest of the wave traveling? That would be the speed of the wave. You could also ask how fast the particle is traveling, right? How fast did you kick the football? So both of them kind of have this property of speed. Now let's look at a slightly more interesting example, I suppose. So this is supposed to be a GIF. I hope that it's playing okay on your screens and is not too laggy. But in case it is laggy, I'll explain what's happening here. There's somebody at the top of the screen right there who is essentially doing a single sort of up-down motion with a rope. And there is a bump in the rope that travels all the way down to like toward us, toward this pole. And then when it hits the pole, it sort of rebounds off and the wave goes back the other way. And then another rebound that's a little bit smaller comes back and forth again. So my question to you would be, does this little ripple on a rope count as a wave or a particle? And if we take a systematic approach to this, we would try and ask ourselves some questions from the previous slide. Is there some aspect of repetition? Yes, right? Because as I said, the ripple travels down the rope once, it bounces back, it comes back to us a second time, and it would keep going in perpetuity if this was an ideal setup. So there is some sense in which it repeats, it goes back and forth over time. Now we can also ask though, does the ripple have a position? And I think it's fair to say that the ripple does have a position, right? You can track where it is as it's coming down the rope and where it is as it goes back. It also has a speed, right? Although that's a property of both waves and particles. But just based on the fact that it has some position and it has some repetition, we would think that this is kind of both, right? It has some properties of both. So as I mentioned before, we can ask the questions, where is the ripple, as well as how often does it repeat? And they both mean something, right? None of them are nonsensical. Okay, so we learned a little bit about the distinction between waves and particles, but we can see that there are some things, even in our world, not quantum mechanics or anything, just in our regular world, that can be reasonably defined as both a wave and a particle, such as the ripples on a rope. Now, in the early 1900s, physicists were wondering whether atoms, molecules, ions, electrons, protons, neutrons, all these really small particles that we knew made up the world around us, they were wondering whether these particles might have similar properties, right? When we draw, even today, when we draw atoms, usually we draw electrons and protons and neutrons and things as points, which kind of suggests that they're particles. And indeed, the understanding was that they were particles for many, many years, until the early 1900s when we started doing experiments and saw that actually they kind of behave more like a ripple on a rope, right? They're not really like a football. It's more like this combination wave and particle object. Okay, so I'm going to stop here for just a moment. There were a lot of messages that flashed by in the chat, I know. But if anybody has questions right now, feel free to send them. And if you did already send your question, feel free to send it again, just so that I see it here. Just if you have any questions on waves and particles and what defines a wave or a particle, both. So one person asks, are waves just mathematical models? I can't get around the fact that there is a ripple progressing across a lake. That ripple is still made of particles. This is a fair point, and we're gonna get to this in a later slide, but you're absolutely correct that this whole distinction between waves and particles is an entirely human defined construct, right? Waves and particles are not two separate things. There is kind of a continuum between them. And so indeed, many things behave as both waves and particles, and the distinction is artificial. And that's kind of the point that we're trying to build up to here. Isn't it just simple harmonic motion of the string, the ripple? Yes, absolutely. And I think this is kind of a similar point as wondering why a ripple on the water couldn't just be considered a whole bunch of particles acting in unison. And I can't really think of an answer why that's an incorrect model. It's totally fair to understand it that way. And yeah, I mean, in the next section, we're going to be talking about how these things are sort of artificial distinctions. Okay, so how a qubit can simulate both particle and wave property, and the question about double slit experiment, both of these I think should be answered when we get to the section on the double slit experiment. So for now, I'm going to move on. I also forgot to end the poll. Oops. Okay. So we ended off with this fact that in the early 20th century, physicists were looking at all these subatomic particles and wondering if they were waves or particles. Let's look specifically at the example of electrons. As I mentioned, when we draw an atom, we normally draw the protons and neutrons, or just the nucleus in this case, as well as all of the electrons as particles. Now, this was basically just an assumption based on some very early experiments, but physicists started doing experiments at that time that showed electrons exhibited wave-like properties. Of course, one of those, as we learned, was the double slit experiment, which I will get onto soon. And so we now know that electrons are a little bit of both. They're kind of like that ripple on the rope. But as I said before, we shouldn't really be thinking about this distinction at all between waves and particles. There is I would think of it as sort of a continuum between things that are more wave-like and more particle-like, but we want to have some kind of way of describing that mathematically. And the mathematical description of how wave-like or how particle-like something is this equation right here. So this is called the de Broglie wavelength equation, and we're going to walk through it sort of piece by piece. So the first section here is the wavelength. So this is the Greek letter lambda, and the wavelength is just going to refer to the distance between crests in a wave. So if I have a wave that looks like this, the wavelength is literally just the distance measured in meters or whatever between two crests of that wave. Okay, the second piece of this is P, which is the momentum. So remember, we're talking about some object, I guess I'll start calling it, and this object is going to have some wavelength property, some wave-like properties, and some particle-like properties. So the lambda is kind of like the wave property. The momentum is kind of like the particle property. So just as a quick refresher, momentum is equal to mass times velocity. And velocity, I know, is kind of a property of both waves and particles, but mass is really the thing here that defines P as the particle property. Now that leaves us with just one letter, and that's H. H is called Planck's constant, and it's just a constant number. I think actually I have it on the next, wavelength, momentum, yes, there we go. Planck's constant, and it's equal to this. So no need to memorize this, of course, you will always be able to look it up. But it is sort of like the defining number that tells us how wavelength and momentum are correlated with each other. So let's do a little bit of practice. Now this equation is kind of magical because you can, like most of the time, you just plug in numbers and you will get an answer that is technically correct, even though it might not fit into our intuitive model of the world. So we're going to ask, what is lambda for electrons? We're given the mass and velocity of a particular electron. So I'm just going to use this formula. Lambda equals h over p. I'm going to plug in my values here. So h is 6.626 times 10 to the minus 34. And then the units here are joule seconds. So joule times second. Divided by, and the momentum is just mass times velocity. So 9.1 times 10 to the minus 31. And velocity is 2 times 10 to the 8 meters per second. So a little bit annoying to write down. I will tell you right now that all of these units cancel out. If you expand what joules are in terms of all the others, this will all simplify out and we'll get something in meters. So the wavelength here is about 3.64 times 10 to the minus 12 meters. And again, you just plug this into a calculator. Hopefully I'm actually correct here, and this is what you would get. So just for some context, remember what we're trying to find here. We're trying to find the wavelength of an electron, right? So an electron, we said, is both kind of a wave and a particle at the same time. And we want to find out, well, if we're supposed to believe it's a wave, what's the distance between any two crests in the wave? And the answer is really, really small, right? 10 to the minus 12. This is about, I don't know if this is going to help at all, but this is about 100 million times thinner than a human hair. So it's beyond anything that you could see with your eye. It's even small on the atomic scale. It's very, very tiny. But that is the distance between waves and an electron. So if I were to draw the actual wave kind of like this, it would be, this super, super small wave pattern where the distance between any two peaks is like microscopic, right? So in some sense, it's very difficult to even see the wave pattern because the waves are so clumped together for an electron. So this brings us to the double slit experiment. How did physicists actually decide that it made sense to describe things as like waves and particles at the same time? So let's walk through this. We start off with a source of waves or particles on the left-hand side. Now, the reason we say waves or particles is because, as we know, everything is kind of both. So a source of anything is going to be a source of kind of waves and particles at the same time. We put in front of that a wall that has two slits in it. And then on the other side of the wall, we have a screen that records what particles / waves end up hitting the screen. Now, this source is going to throw out whatever objects it is making in sort of this wide random cone, right? So picture a cone in 3D. It's just spraying these things out in kind of all directions. A lot of them are going to end up hitting the screen itself, and their journey ends there. But some of them are going to end up traveling through one of the slits and hitting the screen, right? So let's think about how this should look for particles. So suppose that my source is a marble gun, right? So this is just something that literally shoots out marbles, just say, right? Just like that. And as I said, there's kind of this conic spread pattern that comes out of it. We put our double slit in front of the source. We line up our wall. And like I said, a lot of the marbles in this case are going to stray a little bit too far, and they're just going to bounce off the wall, or they're going to hit the middle and they'll just bounce back. But some of them are going to travel through the slits, and they'll have slightly different trajectories, but we should get some kind of pattern appearing there on the wall and some kind of pattern appearing here, right? And indeed, that is what we would see. Well, my drawing is a little bit off, but you see these sort of two groups of particles appearing on the screen. Now, usually when we look at experiments, we will see particles represented as bright spots. So I'm just going to start introducing this notation here that there's two bright spots that appear on the screen because particles hit the screen at those locations. Okay, so what if we do this again with waves? So light, as you might know, travels in a wave. So we're going to direct a whole bunch of light waves toward double slit, just like that. And we're going to see what's called an interference pattern, right? So this is just a little bit of wave physics. When you send a wave at a small opening like this, instead of continuing in a straight fashion, it's going to turn into kind of this like propagating, this circular propagation, much like if you dropped a pebble in the water. So you can kind of imagine that there's been a pebble dropped right there and a pebble dropped right there. And what you're seeing here, these lines are the crests of the wave moving outward. Right, so it's a little bit hard to imagine this because it is a three-dimensional picture, but each of the lines here just represents the crest of one wave. Now, we're going to put a flat screen in front of it, and what you notice is that you get this pattern with multiple bright dots. And the simple reason for that is that if I sort of draw a line anywhere, right, imagine putting the screen somewhere in this interference pattern, you'll see that there are intersection points kind of roughly on a line. And those intersection points are where crests will overlap, they combine in intensity, and you end up with these bright spots. In between them, you have troughs overlapping, and those spots will be dark. So as you see there, bright, dark pattern. This is what we call an interference pattern, and it's sort of the characteristic behavior of a wave. So here's a quick animation just to show what's going on here. Again, the way that this works is all of the sort of light sections are meant to be crests of waves. All of the dark sections are troughs. But here, instead of showing the individual wave patterns coming out of each slit in the double slit, we are just showing what the combination looks like, right? So this is what you would get if you tracked where all of the crests sort of interact with each other and constructively interfere, and where all of the troughs sort of destructively interfere and cancel out. And so this also shows you how you get sort of these bright and dark patterns. I think this is a very pretty animation to look at. All right. So I'm gonna, oh, whoops, went one too far. I'm gonna start introducing some nomenclature here to describe what's going on. The first letter is going to be a distance capital D. So capital D is going to be the distance between our double slit and the screen where we're measuring. Now, for all of the calculations that I do coming up, we're usually just going to assume this is 1 meter. It doesn't matter too much. The second one, which is going to matter more, is the slit distance. So this is basically asking how far apart are the two slits, and that's going to be small d. By the way, I know it's confusing to have 2 letter Ds in this. We're going to get to an equation soon, but this is just to kind of keep consistent with how textbooks and things usually teach it. The final bit that we have is the wavelength. So lambda, which is the Greek letter we had before, is just going to be the distance between any 2 crests, right? So in this picture, it would be the distance between any of the black lines or any of the white lines, and it's the same. We put all of these together in an equation, and we get the spacing between the light and dark spots. So the spacing, I'm not going to derive this, but the spacing S is just, again, the distance between, say, the 2 bright spots, or equivalently, the distance between 2 dark spots. And it's given by capital D lambda over small d. So just look at this for a second to get sort of an intuitive understanding of how it works. The main thing I'm going to point out is that as the slits get further apart, so small d gets larger, the spacing is going to get smaller, right? So further slits means there's going to be less spacing on the interference pattern. Okay, so let's do a couple of calculations to see how this works. Problem number 1. What is the spacing S if we have a distance, capital D is 1 meter, like I said, a slit distance of 1 millimeter, and we use red light, which is 800 nanometer wavelength? We have some unit conversions up top here. Just give me 1 second before I continue. Okay, so let's get back to this problem. Now, I'm just going to go ahead and use the spacing formula. Start off with S equals capital D lambda over small d. And then we are just going to plug in our numbers. So capital D here is going to be 1 meter. Lambda is going to be 800 nanometers. I'm just going to convert this right away to use scientific notation. So it's 800 times 10 to the minus 9 meters. And then we divide that by small d, which is 1 millimeter. Again, I'll convert it to scientific notation using this. So 1 millimeter is going to be just 1 times 10 to the minus 3 meters. Now, I find it's good to get in the habit of doing these conversions just so you never accidentally, keep it as 800 here instead of 800 times 10 to the minus 9. So here we get 2 of the meters cancel out, and then our result is just going to be in meters, which is as expected. The spacing is just the distance. So if you go ahead and plug all of this stuff into your calculator, you are going to get 800 times 10 to the minus 6 meters, which is just 800 micrometers. Again, I hope I'm correct here. All right, so what does this tell us? Well, remember we have a setup where small d is 1 millimeter. So we have our double slit, the distance here between our slits is 1 millimeter. 1 millimeter. And we're sending some waves at it. And these waves, actually, I should draw them much, much closer because they're only 800 nanometers apart. So these waves are like super, super close compared to the spacing of that slit. We send these waves at the double slit, and we get some kind of interference pattern on our screen. And the spacing between the light and dark parts, so I'll just kind of shade in the dark parts here, and so on, right? The spacing between any of these parts is going to be 800 micrometer. So actually, again, my drawing was pretty bad. These should be way closer together than that slit. Okay, so let's continue. We're going to go on to a second problem. So very, very similar. Capital D stays the same. We're still using red light, which is 800 nanometers, but this time the slit distance is going to be 10 millimeters. So I'm going to go ahead and throw a Zoom poll up on the screen. I want everybody here to try this for yourself. Go ahead and give it a shot. So I'm going to launch a poll. Go ahead and put your answer on that poll once you're done the question. And once a few people have started to answer, I will go ahead and do the question myself. So again, just as a reminder, this is the magic formula to use. Oops. This is the formula to use. And then the only other complicated part here is going to be converting your units. So just make sure that you're careful with that, and you should get the right answer. So I'll give just a couple of maybe 30 seconds to a minute here. And feel free to ask questions in the chat if you have any as this is going on. So interesting questions here. I'll go to the first one. Somebody asks, without this type of physics, can we still use quantum computing? I think my answer would be yes, that you could use quantum computing without understanding the physics. It just wouldn't make a lot of sense. You would have to just kind of accept as fact some of the postulates. Here, we're hoping to give you a little bit more of an intuitive understanding of where some of these facts come from. That's kind of what we're building up to. What will be the pattern if the number of slits tends to infinity? Yeah, good question. So if the number of slits tends to infinity, let me just try and think. So what you would have there is a whole bunch of slits, and you would have sort of like these circular propagation patterns coming out of each of them. So the way that you would kind of try to visualize this is, where do all of these overlap with each other if you have infinitely many of them? I'm not 100, like I don't know the answer off the top of my head, but I wonder if it would be a similar pattern, just kind of looking, you would still get overlaps happening kind of along a line. But I'm not sure. I'm not exactly sure what would happen in that case. Okay, so sorry. I'm sorry, I won't get to any other questions because most people have answered the quiz. So I will go ahead and just do it quickly myself. It's a very similar formula. So I'm going to do the same setup. 1 meter as capital D, 800 times 10 to the minus 9 meters for our wavelength. The only thing that's different now is we have 10 millimeters instead of 1 over here. So it's 10 times 10 to the minus 3. And so here we're going to get something that is 10 times smaller. So it's just going to be 80 micrometer. Now, for some sort of like context on what this means, oops, I drew over it. So the human eye can resolve features, so differences, I guess, differences that are at least 300 micrometers apart at a distance of 1 meter. So one way to imagine this is if I'm sitting a meter away from my computer screen, I could see the difference between two pixels if they are more than 300 micrometers apart. If they're closer than 300 micrometers about, then your eye can no longer tell the difference between the two pixels. So a good way to sort of get a feel for the double slit experiment is to think about what parameters will allow you to see the spacing, will actually allow you to see the interference pattern. Because you can imagine if you are looking at one of these bright, dark, bright, dark, bright, dark patterns, and the spacing was too small, the bright and dark, repetition was too fast, you would just see like a gray band, right? You wouldn't actually see any interference pattern. So we actually see that difference here, where if you're using red light and you use a slit distance of 1 millimeter, this is indeed this is actually going to be like, you can see this, right? The distance between the bright and dark patches is larger than our magic 300 micrometer number. And so you would be able to see a definite repetition between light and dark patches. But if your slits were too far apart, so for example, if they were 10 millimeters apart, you would no longer be able to see the interference pattern because the spacing between them would be too small. I hope that made sense. That was a bit of a weird explanation, but okay, let's go on to another problem. We're just going to flip this around a little bit. Now, here we have a drawing of the double slit experiment. We have light coming at our wall with the two slits. What if we turn that into electrons? So in the previous example, we had red light. Now we're going to try firing electrons at this wall. So again, same problem, same equation that we're going to use. It's up here at the top. Now this wavelength here, by the way, we do give it to you here, but you'll notice we actually computed this on a previous slide. When we introduced the de Broglie wavelength, we calculated the wavelength of an electron. That is this number. Hopefully I got it right. Okay, so we're just going to go ahead, use the same equation. I'm going a little bit faster through this just because, again, it's just kind of plugging in numbers. I think the more important piece with all of this is understanding what these equations mean, right? Plugging in the numbers isn't really the interesting part. So capital D lambda is 3.6 times 10 to the minus 12 meters, divided by the slit distance, which is 1 millimeter. Now, if you work this out, you should get something around 3.6 nanometer. Now, 3.6 nanometers is much, much too small to see, right? So our limit, remember, for what you can see is something that is 300 micrometer. So this thing is like several orders of magnitude off. So if you were just trying to look at the screen with your naked eye, the distance between these light and dark patches would be so small that you would basically just see a blur. So let's flip this question around and ask, what spacing between the slits would we need to be able to see the interference pattern? So we'll use this number 300 micrometer as sort of the standard definition of the eye. And we'll use the same formula. We just need to rearrange it now. Now we have a target spacing. We know how far we want the light and dark patches to be from each other. We know how far we are, and we know the wavelength of an electron. What we want to solve for is how close our slits need to be. So I'm just going to multiply both sides by small d, divide both sides by s, and we get something that looks like this. And then I can go ahead and just, again, plug in my numbers. Easy stuff. Again, this part is not too interesting. The S that I'm going to use here is, again, the definition of the eye, which is 300 micrometer. Okay, and now if you go ahead, plug this into your calculator, you will get 1.2 times 10 to the minus 8, which is 12 nanometers. So let's take a step back. What are we calculating here again? 12 nanometers has to be the distance between your slits. So in order for you to see electrons interfering with each other on the screen, your slits have to be super close together. So just to give some idea of what size this is about the width of DNA. So that's not like the length of DNA, because DNA is many meters long. This is the width of DNA. So if you had your little double helix pattern, that would have to be about the distance between these two slits for you to see anything. So the natural question next is, how do you do that, right? These slits are so close together. It would be very difficult to manufacture something with slits that close. Is there anything else we can use? And the answer is yes. Usually what is used in practice to actually do this double slit experiment, just as a quick reminder here, this is a schematic of it. But again, in real life, we're now saying these two slits have to be super, super close together, like the width of DNA. So on a molecular level. And so indeed, what we will usually do is we will use a molecule to get it. Oh, sorry, I'm kind of out of order here. There we go. That's the picture I wanted. So what we'll use for these slits is actually literally the gaps between atoms in a crystal. We use a crystal just because atoms are regularly spaced inside of a crystal. And so here you can see an electron microscope image of a crystal. And you can see how the atoms sort of line up nicely. And there are ways of doing experiments where these lines formed by the electrons are effectively your double slits. As you can see here, of course, there's going to be many slits, but we can kind of imagine it the same way, that you're going to try passing electrons through this crystal, and it'll have the effect of slits that are very close together. So you can see here, the scale is 3 nanometers. So these slits are going to be like, half a nanometer apart or something like that. What we have here is the picture of an actual interference pattern of electrons. So this is literally what it would look like if you had a screen that lights up every time an electron hits it. You would see these definite bands appearing where the electrons have hit the screen. Okay. So we talked about electrons passing through a double slit. Just for a little bit of fun here, right at the end of the lab, let's talk about how crazy it would be if a human was passed through a double slit. So I know that all of you had Rahul, or I think a lot of you had Rahul as your TA last semester. So we're going to try passing Rahul through a double slit. See what happens. Because again, everything is waves and particles. Surely a human also behaves as a wave to some extent. So let's see what kind of numbers we get when we do this. Now, the first step here, before we can use the formula for S, is to get Rahul's wavelength. So just as a reminder, we're going to use the de Broglie wavelength equation, where we have Planck's constant on the top and momentum at the bottom. So we're going to get Rahul to sprint really fast, 8 meters per second. That's pretty quick. He's going to sprint really fast at the double slit. Suppose that Rahul weighs 70 kilograms. He's running at 8 meters per second. The question now is, what's his wavelength? Which I know is super weird. This is the weirdness of things being both a wave and a particle at the same time, but this is a reasonable question to ask. So I'm going to give you a chance to practice. Here is a poll. And the question again is, what is Rahul's wavelength? So go ahead and give this a shot yourself. See what answer you get. I just gave ranges on the poll, not exact answers, but I will solve this once everybody here has had a chance to give it a try. And I will also try and answer some of the questions that were flashing by as we do this. So yeah, one person asked, will there not be any chemical reaction as the electron passes through the molecule? To be honest, so I'm a computer science person. I don't know the technical details of how that would work. I would imagine that you would have to do some kind of special preparation to make sure that doesn't happen. Why are the images in black and white? That's a good question. So the reason the images are in black and white is because because of what the screen is, basically. We've just been calling it this, a screen without explaining too much more what that means. But usually it's a material that is going to undergo some kind of chemical reaction when an electron hits it. And the chemical reaction is going to cause it to fluoresce. So it's going to change color or give off some light when an electron hits it. And if it fluoresces, for example, it gives off light, you just have a camera that picks up where all of the flashes of light are coming from. And so the natural way to present that is just, flashes of white are the light of the electrons hitting the screen, and dark patches are where no electrons have hit the screen. Oh, can I share poll stats? Sure, yeah, absolutely. So one person, seems like people are still working on this problem, so I'll answer one more question. Somebody asks, they say that they saw a YouTube video the other day in which they said that when we observe the electrons form an interference pattern, but when we don't, oh, I see. But when we don't see the electrons, it moves as particles between the slit. Right, okay. So there is this issue of what happens when you observe. Now, we aren't going to get into this right now. Oh, actually, somebody just asked this question as well, where you observe the particle and wave behavior simultaneously. Oh, actually, slightly different question. To answer the original question, this experiment does behave differently if you watch one of the slits. So there's actually going to be a video in sort of like the additional resources section of this presentation, which I would highly encourage people to watch, that explains some of the weirdness, because the basic idea is that when you do the experiment without checking which slit the electron goes through, you get it behaving like a wave. But as soon as you start looking at one of the slits to be able to tell whether the electron went through the left or the right, then it starts behaving like a particle again, which is very strange. And to be honest, the interpretation of that is kind of a philosophical question. There's many different interpretations. But yeah, there's a video at the end that I will recommend as additional content. Okay, so it seems like a few people have had a chance to answer this question. I'm going to start walking through it. Now, again, the equation part of this is pretty easy. It's more a question of interpretation and figuring out what exactly you're supposed to plug in. So we want to solve for Rahul's wavelength here, lambda. Now we can just plug in h and p. So h is always just a constant. You can always just look it up. So I'll put that on top. Now p, momentum, is just going to be the mass times the velocity of our particle wave object, right? So Rahul's mass is 70 kilograms. And Rahul's velocity in this example is 8 meters per second. Okay, so if you plug this into your calculator and you don't make any mistakes, or hopefully I didn't make any mistakes, you should get something like 1.18 times 10 to the minus 36 meters. So this is extremely small, to say the least, right? Before I was comparing to the width of DNA and human hair and that kind of stuff. I mean, at this scale, 10 to the minus 36 meters, I have no idea what the comparison would be, right? This is just ludicrously small. It's many hundreds of millions of times smaller than an electron even, right? So again, what that actually means intuitively is that Rahul's wave, if I drew him as a wave, would be ridiculously closely spaced together, right? Nothing would be able to see the actual distance between the crests on that wave. And so it would kind of merge into just this solid mess of waves that you cannot actually distinguish. And for me personally, I find this kind of helpful to imagine why a large object like a Rahul behaves more like a particle in a lot of ways, because the waves are just so closely spaced together that any wave-like behavior is just not detectable by pretty much anything, right? Because the waves are just so small. Okay, so we promised to run Rahul through the double slit experiment. This was just step 1. Let's now move on to step 2. What is the slit distance? How close do these slits need to be if we want to actually see Rahul's interference pattern. So this is the last question of the day, so it's a little bit tougher. But I'm going to throw up a poll and also remind you of some of the numbers we had before. So just as a reminder, we found on the previous slide that Rahul's wavelength is 1.18 times 10 to the minus 36 meters. And the distance, the slit distance that we need, S, has to be at least, and we'll just use the number for now, 300 micrometer, which is 300 times 10 to the minus 6 meters. Or I'm sorry, was it nano or micro? Oh yeah, it's micro. Okay, I have a mistake in my notes, but that's fine. I hope Rahul's wavelength is doing very well. Yeah, so go ahead, try plugging in these numbers. We have the wavelength. Oh, I guess I should say the distance capital D here, we're still just taking that to be 1 meter. So kind of just don't worry about it. And we want to find what is the small d that we need to see Rahul's wavelength. So I'm going to give another sort of like minute or so for everybody to give this problem a try. I'm going to scroll through the chat a little bit as well. Oh yeah, somebody mentioned the photoelectric effect. That is an awesome example, because a lot of what we're talking about here with the double slit experiment tends to be particles behaving like waves, which is one way to show that things are both waves and particles at the same time. The photoelectric effect, if you're curious and want to look it up, it's an example of a wave, light, behaving like a particle. So it's kind of like proving it in the other direction. So, oh yeah, so somebody asked, is there an experiment to observe both particle and wave behavior simultaneously? I would say that the double slit experiment is probably the best you can do, where the interference pattern tells you that the electron must have been a wave at some point. But, well, actually, this is kind of the optional content where we'll talk about the single electron experiment. But I think the very short version of that is that you get this same pattern even if you fire the electrons one by one. So each individual electron travels as a wave through both the slits and then hits the screen at only one point. So it's not exactly simultaneously because first it travels, then it hits. But I think that's, I think, at least in my knowledge, that's the closest you can get. If anybody else has thoughts on experiments, though, I'd love to see that. Okay, so about half of you have had a chance to answer this question, so I'm going to go ahead and start answering it myself. Now, again, I'll just rearrange this so that we are solving for the distance small d, d lambda over s. And then we just plug in our values. So capital D is going to be 1 meter. Lambda, so remember lambda we solved for before using the de Broglie wavelength equation, which was 1.18 times 10 to the minus 36 meters. And then we're aiming for a slit distance of 300 micrometer. So 300 times 10 to the minus 6 meters. Now, what I got in this case is going to be off by a little bit. I think it should be 4 times 10 to the minus 27 meters, roughly. I have this wrong in my notes, though, so I might have done that incorrectly. No, actually, I think it should be the other way. I think it should be 10 to the minus 33. Anyway, you can just plug this into your calculator. I will post, actually, so somebody's saying 25. I'll post the corrected version afterward just to double check. So this will be correct in the notes that I send you when I post the slides. Anyway, regardless though, the answer should stay the same, closer than 10 to the minus 25, which means you would need slits that are almost impossibly close together to actually observe Rahul's interference pattern. again, just to kind of remind you, when we had the picture before of the actual atoms inside a crystal, they were kind of like half a nanometer apart. I mean, an answer like this is, again, like 100 billion times smaller than that, right? It's ridiculously close together. It's way closer than atoms inside a molecule. It's way closer than electrons inside a nucleus. To see Rahul's interference pattern, you would need slits that are ridiculously close together. And I think the moral of this story is just that, the reason we don't see humans behaving as waves is that the numbers you would need, the distances you would need to see any wave-like effects are just impossible. They would never happen in our world. And so we never see humans behave as waves. All right. So that brings us to our key takeaways, which is just a quick summary before we end off here. First up, we learned that particles and waves are essentially human-defined buckets to make sense of the world around us. Physics doesn't really care. Physics thinks that everything is both particles and waves. And the way that we relate those two things is through the de Broglie wavelength equation. So again, this kind of gives us a correlation, a relationship between waves on the left and particles on the right. We learned that pulses and ripples, remember the ripple on the rope, can possess both particle and wave-like properties. And then we found that in the 19th century, in the 20th century, physicists discovered that pretty much everything on the nanoscale behaves like a ripple on a rope. And then, like I just said before, the de Broglie wavelength equation is how we relate these two characteristics. Okay, so I will stop for any questions. And I know I did not get to the Hamiltonians and that kind of stuff. I do plan on answering that right now, basically. I just wanted to try and get through the required content on time. So if anybody has any final questions on, I guess the two main takeaways from this last part is the de Broglie wavelength equation and the slit distance equation, right? If you know these two things, you should be able to solve all of the questions of this type. Okay, so any questions? Feel free to throw them in the chat. Okay. Yeah, so this, what Christine says here, basically the smaller the wavelength, the less prominent the wave properties are. Absolutely. I think that's a great way of thinking about it. And the more intuitive you can get these two equations, like if you can kind of build them into your head as intuitive facts, that's when quantum mechanics starts to make at least a little bit more sense. All right. So Hamiltonians, yes, let's talk about that. I will just offer one more quick reminder. This entire thing is recorded. So if you do want to watch any part of it over again, you're free to do so. So let's talk about Hamiltonians briefly. Now, unfortunately, I was not in the lecture, so I don't know exactly what was taught. But the Hamiltonian is important primarily because of Schrodinger's equation. So I'll do just a very brief review of that. So Schrodinger's equation is probably one of the most famous equations in quantum mechanics. And what it looks like is basically this. There's a few different, oh man, that's a really bad sigh. There's a few different formulations of it, but this is kind of the most standard formulation. Now, I'm going to kind of just ignore the I and the H bar. They're just constants. You use them in a calculation, but it's not important to understand what's actually being said here. The key thing to look at is this relationship right here, okay? And I kind of like to imagine it actually in the opposite order. For me, it makes sense to just define it in the opposite order. So what we're really saying is, we want to understand what a Hamiltonian is. H here is a Hamiltonian. And the way that I think about this is we're defining the Hamiltonian to be the derivative of the state. So however the state changes in time, that is what the Hamiltonian defines for us. And like I say, I like to think of this as essentially a definition, right? So I know that a lot of you might be in high school, probably haven't learned differential equations, but I think the sort of summary of why differential equations, diff-EQs, are so important in mathematics is that any system that changes over time, which pretty much everything is a system that changes over time, can be defined by differential equations, which is to say how it changes, how fast it changes, how the rate of change itself changes over time, right? And so any changing process is going to have some fundamental characteristics defined by differential equations. Here, the fundamental defining differential equation that tells us, hey, how do things change in time, right? Our quantum state could be anything. It could be an electron, it could be a proton, it could be a superconducting qubit, whatever. And what the Hamiltonian tells us is how it changes in time. How does it evolve in time? How does the system change? What will the system tell us at the end of its evolution? All these questions, the reason Schrödinger's equation and the Hamiltonian is so important is because it encapsulates all the information about how your quantum state changes. And for our purposes, I mean, usually we're quite interested in sort of predicting what a quantum state will look like at the end of a process. And to do that, you need to know how it changes throughout that process. So in summary, I like to think about the Schrödinger equation in sort of a simplified form like this. The Hamiltonian is the definition of how our state changes over time, which is kind of like the most fundamental question you could ask about any physical system. I know that's pretty high level. I'm not going to go into any more math with Schrödinger's equation or Hamiltonians, just because I, again, unfortunately don't know exactly what was covered. But frankly, like understanding what a Hamiltonian is, it took me a very long time to get that. And I hope that was a decent explanation. But yeah, I think the best way to think of it is just it's the defining characteristic of how things change. And that's why it's so important. Okay, so are there any other questions before I move on to optional content? And again, for anybody here, if you need to hop off, no hard feelings. All of this is recorded if you really want. And everything that comes after this, I mean, even that discussion about Schrödinger's equation, totally optional. So feel free to jump off if you need to. I also said I would share results of these surveys, which I totally forgot to do. So there is the results of the last one. I'll make a note for myself, try and remember to do that. But all right, so let's move on to, actually, I'm just going to take a quick drink of water and then I'll move on to the optional content. Okay. Oh yeah, shoot, sorry. I forgot to do the post-lab feedback. Hey. Got too excited about Hamiltonians. Okay, so for everybody who's still here, why don't we go ahead and do the post-lab poll, just to see how your understanding has changed. So you should see the same question, scale of 1 to 5, how you understand things this week. Yeah, and I think the best summary of everything we talked about here, like this lab was a little bit weird. It was a lot of just me talking and explaining things. But from the mathematics side, like I said, if you know how to use those two equations, the de Broglie wavelength equation, the slit spacing equation, then you should be good to go. All right. So as I promised, there are a few additional readings here if you would like. This first one here, and so by the way, when I post the slides afterward, you'll be able to click all of the links on here. This first one here is the YouTube video I was talking about that shows how observation changes the double slit experiment. It's a cartoon, and so it's kind of silly. But despite the fact that it looks like it was created for 10-year-olds, I think it's actually a really great explanation of this experiment. So I would encourage you to watch it. It's only a few minutes long, so it doesn't take too long. The other two here are readings, just if you want more detail on the double slit experiment. It is one of the most beautiful experiments in physics. It was voted that a couple of years ago. And so there's a very rich history behind it. So if you want to read up on any of the history or more details on this experiment, it's a really, really neat one to learn about, just because it's defined so much of physics. Okay, let's move on to the optional content. So the optional content is pretty quick this week. It's just to sort of bring up an important technicality, I guess, with the double slit experiment. So before I was kind of, I wasn't very specific with exactly how our gun worked on the side here, right? So with our electron beam gun, how fast does it shoot electrons? I told you that it shoots them out in sort of this conic pattern. Some of them are just going to bounce off the double slit, but some of them will pass through. The question, though, is, well, how fast were we firing the electrons? Does it matter how fast we fire the electrons? Because when people first did this experiment and they saw this interference pattern, they thought, well, maybe the electrons are being fired out so fast that they interfere with each other, right? So maybe they behave like a wave, but really they're interfering with each other, not with themselves, right? Interfering with itself would be a very strange thing indeed. So the thinking for quite a while was that the electrons were fired out, in such rapid succession that they bounced off each other, they interfered, and somehow that bouncing off each other causes this interference pattern. And people had all kinds of different theories. So the natural way to settle this confusion, this curiosity, was to try and shoot electrons one by one, right? So we're going to modify our electron gun to fire a single electron, wait like a second, it appears on the screen, okay. Fire a second electron, wait a second, it appears on the screen, so on and so on. And so this experiment, literally takes hours because you're waiting a second or so between every electron. And we want to get a large number of electrons to appear on the screen to reveal what pattern they make in general. So this is what you end up seeing. Now, this footage is sped up, obviously, so we're not sitting here for hours watching what happens. But you should start to see as we fire single electrons, one at a time. So again, this is not, a gun shooting tens of thousands of electrons, kind of like a fire hose. This is one electron at a time being fired at the double slit. It's just sped up for us to see here. So it takes a little while to emerge, but you should definitely start to notice that there is some kind of banding pattern here, right? You can start to see that there is a light band here, there's a light band here, there's a light band here. And there are definitely dark spots in between those. And if you fired more electrons at this screen, you would just see this pattern become clearer and clearer over time. So this was really surprising, right? Because we saw that even when we fire only a single electron at a time, we still get the interference pattern. And so the only reasonable, although it sounds insane, conclusion at this point was that electrons are not interfering with each other. They must literally be interfering with themselves. A single electron must pass through both slits, interfere with itself by becoming a wave, and recombine back into a single electron when it hits the screen. Which, like I said, the intuitive explanation for this, there basically isn't one. There's a few attempts, right, to explain how this works. But the best way that we understand it at this point is really just that as the electron is traveling, it's a wave. And then as soon as it hits the screen, it collapses. Sometimes you'll hear that term. It collapses into a single particle, a single dot that appears on the screen. Now, there was a question, what do you mean by single electrons? Yeah, good question. I mean, in the classical picture, right, if I were to draw an atom with the nucleus and a bunch of electrons orbiting around it, a single electron would just be, one of those. Now, how you produce a single electron gun is not something that we'll go into here. It's pretty advanced technology for an actual lab. Although the idea behind it is not too complicated. But we're just imagining that we can create a stream, just a single electron, release it into the world, wait a second, release a single electron again, and so on. And you still get the same interference pattern. And so, this is the weirdest result you could have asked for, because what people were expecting was that you would just get two bands on your screen, right? Because if you just fired a single electron at a time, it either goes through the left or the right, right? Like that makes sense. Unfortunately, that's not how the world works. Quantum mechanics is much weirder than we thought, and we are still, frankly, only starting to understand how complex it really is. So that's it for the optional content. I am happy to stick around and answer any questions that people have for a few more minutes. But as I said before, feel free to drop off. Thank you all for coming out to this lab, and good luck with the homework. So question is, when we say we're releasing a single electron, maybe it's actually a wave and doesn't need interference with itself while it approaches a slit. Yeah, I mean, that is a reasonable explanation as well. The question then, though, is, well, I guess you would have to start explaining how the electron gun works, right? Because there are ways of designing electron guns where you know with confidence that only a single electron has been emitted. And so I guess it's kind of like the ripple, it's kind of like the ripple on the rope example, where you only have, like, it is kind of a wave, but there's only a single wave. So it's weird, because how do you do an interference? How do you draw the interference of a single wave? That doesn't really make sense either. So I mean, I would encourage you to think about it more on your own and try to come up with an intuitive explanation for it. And if you think you have an intuitive explanation, go ahead and post it on Piazza. Chances are it might be a good explanation, but it's probably technically incorrect in some way, because people have been thinking about this for many decades now. And the reality, it seems, is just that there really is no great way of explaining how this works. So yes, very strange indeed. I saw one person ask about the meeting code. It is always down here in the bottom right of the screen. So if you do come in late, you can fill out your attendance quiz there. Once an observation is made, and again, if you start the experiment, any chance that the earlier observation affects the next outcome? Yeah, no, that is a great question. I mean, the answer we know now is it does not, right? So each of these electrons is independent, and it's a random event. So there is a super small chance that you would do this experiment and all of the electrons would land in that center band, for example, right? It's just the same as saying, if I rolled 10 million die, there is a very small chance that all of them would be a 6. It's just a super small chance. And so each of the electrons, where they end up on the screen, is an independent random event. Okay, so the electron, somebody asked, the electron only ever interacts with the screen, and that's when we see it as a particle. I mean, I would say that it interacts with the double slit as well, right? Because it might start off as a straight wave, like how we saw light being represented in the previous slides, but it turns into the sort of like circular propagation waves after it goes through the double slit. So there is some kind of interaction there, but you're correct that it's not observed. So we might get more into this later in the course, but observation in quantum mechanics is a very controversial subject. Again, watch the Dr. Quantum video on the additional reading slide. It explains some of the weirdness, although it doesn't really go into why the weirdness happens, because again, we're still trying to figure that out. Oh, the small d for this experiment. That is a good question. I'm not sure, actually. I bet you'd be able to find it by going to that link there. I will caveat it by saying these images taken here might be taken themselves with a microscope, or at some magnification. So it could be that the distance between these bright spots you're observing is less than 300 micrometer, but we're able to see them just because we've magnified it. But these are actual electrons. So one thing I can say for sure is that the lambda here was, well, I don't quite remember, but I think it was like 3.6 times 10 to the minus 12, something like that. These are electrons. And so the wavelength of these particles is extremely small, which means either these slits are very close together, or which means either the bright spots are very close together or the slits used in this experiment were very close together. Yeah, so one person says, did you mean that a single electron gets through both slits and is noticed only as a single unit when observed on the screen? Yeah, I think that's a reasonable way of explaining it. That when it's a wave, it travels through both slits, kind of like how, if you, when you pass a wave through the two slits, that single wave turns into two circular propagations. In the same manner, the electron passes through both slits, but by the time it hits the screen, it turns into only a single particle. I think that's a fair way of explaining it. Why is observation weirder than any other interaction? That is another philosophical question. The way that I understand it, which, there is even controversy about this understanding, is just that observation, in some sense, requires you to interact physically with a particle, right? So even if I were to like shoot a marble in a dark room, right, and if I had no way of observing it, maybe the marble will behave like a wave, right? But to observe it, I have to turn on the lights, and maybe the very act of a photon hitting the marble causes some change, right? Or maybe I don't use light, maybe I use like a radar, right? But radar still has to send out light waves that are going to bounce back. So any method of observation, you could imagine that there's a physical interaction that takes place to do that observation. And perhaps there's something special about that physical interaction that's going to, crunch our electron back down to a single point. Will the collapse be explained in more detail later in the course? I think it already has been sort of in the first half. So the rule we learned where the probability of observing a quantum state it looked something like this. So for example, the state psi, the probability of observing the state psi in the state 0, like as a 0, was given by this. And so that is effectively the probability of a collapse. Please answer this question. Where is that question? What about the interaction of electrons with electrons bounded with atoms? Yeah, that's a good question. So usually the actual material that makes up the double slit is going to be atoms, which of course at such a small scale are just nuclei with electrons. So this might not be technically correct, but again, this is just the way that I sort of think about it, is the physical interaction of these electrons is basically just like a Coulomb force, right? Like electrons repel each other. You might have heard this argument for why, like if I push my hand up against the wall, why doesn't my hand pass through the wall? Because an atom is like 99.99% empty space. The actual force that you're feeling pushing up against the wall is actually just the repulsion of negative electrons on negative electrons. And so, whoa. Something just happened on my screen. I hope we're still okay. Yeah, so it's just the negative forces. And so here you're right, that perhaps the interaction of electrons with electrons bounded in atoms is part of what causes this collapse. The real answer is that all of these things have to do with it, because everything, this is getting a bit philosophical again, but technically speaking, everything in our world is the same quantum system. It is all entangled with itself. It is all in a superposition with itself. Everything interacts with everything at all times. And for us to ever fully understand that interaction is probably impossible. And so a lot of what we're learning here is just simplifications that are good enough to do experiments in the real world. Okay, let's see. What about, yeah, okay, so I answered that question. What is the application or solution that using this electron slit experiment? Well, this experiment here was literally just done to show that electrons shot one at a time would still produce an interference pattern. There's not really any further application to it than that. It's just an interesting fact of physics that has, of course, led to many, many other developments. I don't know if that's a bit of a short answer, but okay, I think I answered most questions. Maybe feel free to copy paste your question again if I did not. Yes, that is a very philosophical way of saying every entity is a single unit. But there is actually a mathematical, physical reason to believe that everything is connected on a quantum level, which is kind of cool, if you ask me. Awesome. All right, so I think I will wrap things up there. Thank you all for sticking it out to the end. I hope this was interesting. Good luck with the homework this week. And once again, if you run into any problems at all, post on Piazza. I promise we'll be there to help you. So have a good day, everyone, and we'll see you next week.